cloud. Okay, that will disappear a little bit. I haven't worked out how to not have that appear on your screen. It should be on mine, really, shouldn't it? Can I move it? It will go small in a minute. Apologies for it. Oh, and there's a lecture that I'm supposed to be turning. First of all, thanks for attending the course. I mean, I have to say that I'm a little bit nervous about giving this course because we're being quite ambitious in terms of what we're going to try and communicate to you. And I'll explain why. And this lecture will set the context for why. So we're going to need your help in doing that. So we're very happy to get constructive feedback as we go through and for you to tell us where you're having problems or where things aren't clear. So one of the things is we've just seen there's a link. So it's Carl Henrik and myself that are lecturing. And Carl Henrik used to do this in Bristol, and we've adopted this thing that we've got a Reddit forum. Obviously, if we've got problems, we can solve them with Reddit. And the idea of using the Reddit forum, we've used this across a few different courses and units, is that if you've got particular problems, then sharing them can help. Sometimes some of you will be able to better answer the questions than us, because in some sense, we're trying to do this thing where there's this world out there of data science that we're trying to communicate aspects of that we're somewhat expert in, and we don't necessarily know how to best communicate them. And so by you sharing answers and everything else like that, that will help and leave a resource there for the future. So I was thinking this as I was cycling in. I've never seen data science done well in the real world, never, right? One of the things that I used to think when I was young was that the world was a place where people knew how to do stuff and a safe place where things were being done well and competently. And then as I've got older, I've discovered that's not true. And the reality of the world is it's remarkable that anything works. And there's just a few people doing things quite well. And fortunately, that causes things to tick along. And one space, this is extremely true, is in data science. And why is that? Well, I'm going to give you the context of that today. It's because it's a new and emerging field. And people who claim they know entirely how to solve data science and do it well, they don't know what they're talking about. Because as we develop these technologies, as we get more data and we try and drive data-driven decision-making, we're finding out more and more challenges about that. And you see those challenges in the newspapers, like whether it's, 1 year, it's an amazing thing because Obama has driven his entire election campaign through Facebook, and aren't the Democrats clever? And then 4 or 5 years later, it's like, oh my goodness, Cambridge Analytica have been using Facebook to drive election campaigns. Isn't that appalling, right? These are different things. It's the same idea being applied to the same data and different interpretations as we get better at it or exploit it or do it in nasty adversarial ways. And that's just an ethical side. There's loads of things going on in that space. Now, the aim for me and Carl Henrik is to communicate this to you. And it's hard because we're doing it in 4 weeks, right? And there's a lot to communicate. But when I think we could teach you an easy course where you say, here's 7 machine learning algorithms, and this is how they work, and this is the maths, and we could ask you questions about that, right? That's actually very easy to teach, and that will not equip you at all for what you need to do if you ever choose to become a data scientist. So we're going to do a bit of that, but also a lot of this is how the pipeline works, and these are the challenges you'll face, okay? But teaching that, I've never seen it being taught before. So we may not be doing it in the optimal way. So we'd love your feedback as we try and do that. And a lot of that is going to be through the practicals and assignments. Okay. So what I want to do is spend the rest of today sort of communicating. Actually, I've just suddenly got paranoid. Is the microphone working? Yes, it is. Is give you a little overview of, we've got like a structure for the whole course, but I've decided for the moment, we'll just show you the first part of the course in case we decide we should do some restructuring based on how you're doing with the material so far. So this lecture here, I'm going to try and contextualize everything I've just said. Why is this different? Why is it interesting? Why is it not the same as like my undergraduate mechanical engineering degree or some of the things that you learn in computer science that have been known for a while? And then that'll give the landscape. Then I'm going to move on Monday to the challenges of data science. So what are the challenges that landscape is causing to exist? And then we're going to start then the third lecture, which is listed as 4 here because the middle one's the lab session, on a data science process, which is actually an assimilation of ideas and challenges that I've seen when doing data science pulled together for you to use as you do your projects, okay? The lab session in between, I put 2 up on the website today. One is review and refresher. So one is, here's some things we think you should know probably, but they're being presented again for you to just remember how they work. And that includes things like use of pandas, Jupyter, a bit of probability, a bit of correlation, a bit of plotting, because that's the type of thing that you're going to want to use when you're doing your assessment. So the main assessment, which is on Moodle, do go ahead and look at that now. It's in a drafty form at the moment. It's not 100. We're trying to give lots of hints and tips on how to do some of the tasks, right? The idea is you not to be spending ages browsing the internet. It was me spending ages browsing the internet to work out how to do these things, but to you to see how they piece together to build a data science pipeline. So I think that's mostly true for question 1, which I would urge you can make a start on question 1 question 1 of the assignment right away. You're going to need to refactor it a bit as you go forward, and it sort of says that in the assignment, but you can really start to work on that chunk a bit, because we're both really nervous that you're under workload already. We have to have the assessment handed in by the end of week 8. So we want you to sort of get the bulk of that going and not be under massive stress and pressure to complete the assessment. So please do look at it now. But we will likely refine questions 2 and 3 as we go forward and see where there might be issues and make sure we've got the right hints in there for you. So practical 1 is actually a different data set teaching you how to do some of the things that you're going to be doing in question 1. And that will mirror throughout the course. So the practicals, where we have the ticks, so you have to hand in the practical, answer a few questions about it, are really teaching you the bits and pieces that you will need for the main assignment. So they're very tied together in that way. So just be aware of that and start looking at that material as soon as you can, because I'm aware that you're going to get loaded as the weeks go forward. So for the moment, actually, sorry, that's incorrect. Session 2 is probably still me. So yeah, what happens next week is less important. So the assessment's already available in Moodle, and you'll be able to complete it as we teach. That's the idea, we hope, right? And so if there are gaps, the best thing to do, if you've seen something that you're unsure about on the assessment and you think needs clarification, pop it on Reddit, right? And ask about it. And we'll realize, oh, we weren't clear about how we asked that bit. Or someone else will say, oh, it's just this. You can answer the questions on Reddit as well. And make sure that you're not hitting obstacles as they come up. I often forget to check Reddit. Carl Henrich's really good at it. I'm not even allowed to create, what are they called?
You don't have enough karma.
I don't have enough karma on Reddit. Yeah, so but Carl Henrich does, and I do when I remember I answer questions, or if he sees something I need to answer, he'll drop me an email. One of the things that I want you to get the sense of what you need to do when you're doing data science is this process of refactoring your code, which comes up a lot in software engineering as well. So when you're going to finish your questions, so there's 5 marks for each question, there's 3 questions, and they map to the different stages of the data science process. And then there's 5 marks for your code. And that 5 marks for your code is going to be all about the refactoring and how you structure things. As you'll hear, I've got this analogy I use for data science. It's not programming, it's debugging, right? But it's documented debugging. So imagine you've solved a whole debugging chart, and then you have to worry that someone else is going to commit the same bug. So you have to tell the story about how you solve the debugging, right? That's the thing you have to create as an artifact when you're being a data scientist. So that's the last 5 marks. That artifact consists of things in the Jupyter notebook and things in a sort of Python module, which has a structure that I'll suggest to you that you can use. Okay, so context and landscape. So if you've seen me talk before, you've probably seen me use this quote before, but does anyone know who said this? There are 3 types of lies: lies, damn lies, and statistics. I mean, lots of people say it, but who's supposed to have said it first, I suppose? Anyone? You know, the easiest, when anyone asks for a quote, the first thing you have to say is, it's Winston Churchill. Never normally is, but that's what everyone says. But come on, because I want it to be quite interactive. So someone come up with a name that's not Winston Churchill, any name. Go ahead.
Benjamin Disraeli.
Very good, very good. So it is credited to Benjamin Disraeli. And I think it's a very interesting quote, because statistics itself is supposedly the science of state. So computing numbers to understand how states operate. And Benjamin Disraeli, if you don't know, was Prime Minister of the United Kingdom. The interesting thing, well, there's lots of interesting things about him, including the fact that he was from a Jewish family, but he converted to Christianity because you couldn't, I guess, be a Jewish Prime Minister back in those days. But the interesting thing for the purpose of this is that he died in 1881. So I find that interesting because when we think about the academic field of statistics, what we tend to think about is people like Galton and Pearson and all these mixing in with these nasty sort of eugenics ideas that came about 120 years ago. So what's going on that he's dead in 1881, but he's making this quote? Well, the field of statistics that we think about as being taught sort of down the road in maths is mathematical statistics. It's trying to get around this. So the challenges of statistics is I can present you with statistics and data, and I can cause you to draw conclusions by presenting the data in certain ways. And the field of mathematical statistics is trying to understand when are those conclusions valid and when are they not. So things like randomized controlled trials and hypothesis testing, they all emerge in an effort to deal with this quote. Now, the other thing about this quote is we can find no record of Benjamin Disraeli ever having said this, but we can find who said that he said this, and that was Mark Twain, who was writing in 1904 in his autobiography and credits it to Disraeli. So even if it was Mark Twain that invented it, I mean, he didn't have Google, so you can't blame him if he just said, oh, it was Disraeli. Even if it was Mark Twain that invented it, it's coming from 1904, right? So why is that so important? Because this is my quote. There are three types of lies: lies, damn lies, and big data, right? Because the situation we're in today is very similar to the situation Benjamin Disraeli was in with statistics. Why? Because the situation with data has changed, and the sort of techniques we use to ensure we're not being misled by data have changed. So randomized controlled trials are used for medical validation. Does this drug work? Does it fix people, right? And you randomize the data. But the phenomena we have is we're all working around with massive data acquisition devices. And this is creating a bunch of data that I like to refer to as happenstance data. Data that wasn't written down for the purpose of understanding the answer to a question, data that's just available in the ether. And handling that data is the major new challenge that I think means we can justify the new name of field, data science. A lot of statisticians will say, ridiculous, we've been doing this for years. Well, fine, fair enough, they have. But the reason why we end up creating new fields and giving them new names is because the philosophy by which they were doing it, very, very appropriate and still vital today, is slightly different from some of the ideas that we need to cope with this new wave of data. And that context is what I'm going to give you today. So this is Carl Pearson, who's one of the sort of fathers of mathematical statistics. Other people you might mention would be Fisher, Pearson's son, Egon Pearson. And there's a bunch of people who sort of worked out this stuff. And one of the other things they really did as well, quite famously, is particularly Fisher, they really disliked people who put probabilities over parameters. And they came up with a name to make fun of them. They said they're Bayesians. And so that's what you'll be taught about, Bayesians. But it's this group of people that came up with that name. Why did they do it? Because most Bayesian models are subjective. They're bringing in the knowledge of the prior, the knowledge of the model that's coming from a scientific domain. And they were trying to be objective about data. Yeah, so it actually made sense for the time. Why we're still having that argument today, I don't know, but the argument made sense in the 1920s, 1930s. So one of the things we really need to think about in the long term, and we're not going to solve this, so your picture here, mathematical data science. What is the equivalent sort of set of principles and ideas that we need to be confident about the conclusions in data science? And my partial answer is, my full answer is, I don't know. We can certainly use a lot of the things statisticians came up with, but they don't provide a complete tool set. And while that's happening, you're living in the era of lies, damn lies, and big data, okay? And that's the sort of thing you're gonna have to worry about if you choose to become a data scientist. Maybe you're put off already and don't ever want to see a data science job again. So I want to sort of go down to the sort of fundamentals about why this is a problem. And this idea of sort of talking about this came up because I was trying to do public understanding of machine learning talks. So it's a notion that I call embodiment factors. And it's associated with the ratio of our ability to compute versus our ability to communicate. So I've put a sort of little orange head here to represent human beings. So if you've studied information theory, you'll know from Shannon that you can measure information in bits, and a bit is the result of a coin toss. So if I tell you the result of a coin toss, I've given you one bit of information. You may not know that Shannon also looked at questions like how many bits of information are in the average word in English, and he estimated that it's 12 bits of information. Now, if I'm talking to you at about 120 words per minute, I am communicating with you at about 2,000 bits per minute. And as you'll know, because you're all computer scientists and you worry about your, not all of you, but a lot of you are, you'll worry about how fast your computer is communicating with Fortnite and whether you've got lag when you're trying to shoot someone else. You know, modern machines, well, gigabit Ethernet is quite common, and now even 10 gigabit Ethernet. So that's gigabits per second. So that's 60 billion bits per minute. Okay, so now like these are big numbers. And one way of getting you to think a bit deeper about big numbers is to turn them into money. So given the choice of a salary of $2,000 a month or $60 billion a month, which one are you going to take? And I think that gives you a sense of the scale of the difference, because I think what Jeff Bezos is worth like 120 billion. So you're earning his net worth every 2 months if you're a computer in terms of your information budget. So you're actually up there. You can probably afford to pay for the NHS if you're the computer in terms of your information budget versus your $2,000 a month. So that's off the scale different. You know, it's like totally different from what we're doing when we're communicating. But when it comes to our ability to compute, I mean, things actually flip. So maybe this equation will turn around soon. But if you have a typical computer, and I wrote this slide first, like maybe 3 or 4 years ago, so maybe this number's wrong. About 100 billion calculations per second a computer can do. Now, so that means this interesting thing that I think of as the embodiment. If a computer decided to tell another computer every single calculation it had done in 1 second, so because it wanted to share what was going on, it would take 20 minutes to do it, which is quite a long time for 1 second's worth of calculations. But okay, this is hard. I can't exactly tell you how many floating point calculations you're doing per second as humans. But what I can do is I looked up some estimates of if we would try, and this is, you'll be aware that this is a dangerous sort of estimate that I'm going to give you, but if we needed a computer that was going to simulate your brain, okay? So we're going to have a computer that can simulate your brain. The one that comes closest in the UK is about to be upgraded. It's the Met Office supercomputer down in Exeter that does the whole weather predictions for the UK and the world in the morning and does climate predictions in the afternoon. And you would need something about that size to simulate your brain. And you know, no one's even got these simulations. There was a crazy big European project to do this. Why, I don't know, but there was. So trying to use that for a rough estimate, 1 billion calculations per second is what your brain's doing. Obviously not pure floating point operations, just in terms of your neuron firing. So if you were to try and communicate your neuron firings in 1 second to another human using your ability to communicate, if you even had access to them, which you don't obviously, it would take you 5 billion years to do so. So that really gives you a sort of sense. So that, I don't know, the universe is 9 billion years old, so you'll be here a while. So really gives you a sense of the nature of your intelligence and how different that is from the intelligence we're putting into machines. Because we are stuck with this very narrow bandwidth channel to communicate our ideas. So that's why we're all sitting here. Because if we were computers, I could just transfer the information and you would be done, right? We wouldn't have to spend 4 weeks saying it's a bit like Jeff Bezos's billions and all this sort of stuff. We could just send the facts but all this information needs to be interpreted and understood by humans, okay? So that's the real challenge of data science. So I sometimes like to give this analogy. I was a mechanical engineer as an undergrad because I love cars, and particularly old cars. So now I've got an excuse to show a car. So this is I can't remember the number of the Lotus, it's in the notes, but it's a Formula One Lotus car, and this is the Cosworth engine that powered these things. Of course, very bad, and we shouldn't use them because of climate change, but they're still amazing objects from the 1960s. So I like to give this analogy. I say, cognitively speaking, your brain is like a Formula One engine. It's sort of super, super high performance. But in terms of ability to deliver that performance on the track, you have bicycle wheels. So you have all this power, cognitively speaking. And yeah, so I've shown this is actually, unfortunately, this is, I think, Marcel Renault, who is one of the first Grand Prix, but the Grand Prix in those days was driving across France over 24 hours. And he died shortly after this photo by falling out of that car on a corner because the car skidded off. But yeah, the nature of these bicycle wheels is much narrower than we're even seeing here. Your ability to deploy the power on the track in terms of deliver the things you're computing real time is minimal. Otherwise, we would be the Borg, right? We would have a shared consciousness. We don't, because we're information isolated from each other. So that's really, really important, because compared to us, the computer is less powered. This is a kid called Caleb McDuff who does kart racing. The computer is less powered. It's got a small, winky little computational engine here, but it can deliver all that power on the track. So in some sense, it's doing things in a very different way from us. Like while we're trying to sort of move around the track with our very narrow wheels and our high-powered cognitive ability, the machine just drives around for us. It's totally outside our cognitive understanding, right? It's not actually doing the same thing at all. Sometimes to highlight this to people, I point out that your immune system is an intelligence. Are you aware of your immune system? Is it trying to take over the world? Is it competing with you in any way? No, it's just a different form of intelligence. You thinking that that is true is projecting your intelligence, the one you're aware of, onto your immune system or onto the machine, right? These are very different architectures. But what does that mean for us? Well, it means that in order for me to communicate with you, I have to do this really crazy, weird coding thing, that I have to have a sense of who you are and what you think about the world and what you might know. So within my head, I can model, and a lot of this, some of this is conscious. I might think about how will I do that, but so much of this is subconscious. Like I know that you're human beings. I know the sort of things that will resonate with you. And so by having a model of that, I can decide what to say and I can communicate an idea with you. You, in turn, have a model of who I am, and you may have a model of who you think I think you are, if you see what I mean. It's easier in the diagram, right? And so knowing that, oh, I can get a new version of LastPass as well. It's great. Knowing that, you can come back to me and say, well, given what you said, I want to make a sort of clarification. So you said that. So in order to sort of try and map that onto what I think, I have to say something else, right? And this works really, really well if we have a common shared idea of the world in amongst us. Where it starts to fail is where there are cultural differences. And those cultural differences could be national in terms of where you were born, where you were brought up, what the ideals were, or they could even be which field you're in, whether you're a statistician versus a computer scientist, because people have different objectives in these fields. So your models of each other, you start seeing, oh, you're doing maths. I do maths. You must be doing the same thing as me. Well, very often they're not, because the objective of their field is different. And then when that goes wrong in that way, so when it goes right, it's brilliant, because you're communicating these big ideas with all this sort of information, but you're using the world around to communicate them. You're saying it's like the things you're aware of already in some way, yeah? And so when it goes well, it's amazing, but when it goes badly, it goes really badly wrong. And one of the things you'll find as a data scientist is you have to avoid the temptation to assume someone's trying to do the same thing as you do. Because if you do, then you misunderstand what their objectives are, and you're not listening to what their objectives are, and you end up doing the wrong thing. The biggest arguments I had early career, I realized academically, tended to be between me and statisticians. And the reason was because we used loads of the same techniques, but our objectives were slightly different. So I would wonder, why are you doing that? You know, everything you said up to there was sensible, and then you made this really stupid decision. But it wasn't a stupid decision because they weren't going to the same place that I would have wanted to go to, because the philosophy of the field is different and the culture of the field is different, because they care more about interpretability and I care more about prediction. So these contexts are vital when doing this type of communication. There's actually these great things going back to 1944. So I wonder if this was sort of driven by the prevalence of cartoons at the time. If you watch this video, what you're actually seeing is what? I mean, what's going on here? You know, some kind of argument. Heidel and Simmel wrote all this material where they got people to watch this. It must have been, so imagine they didn't just show it on YouTube. There would have been a projector and then you would have said, and these people would have written things down. What an exciting and expensive experiment. And you know, that there's a fight going on between these, and this one's angry and this one's happy and all these sort of things, right? Well, of course, none of that is true. These are just some shapes on a picture. But because they've been created by another human and who has a sense of humanity, they can communicate ideas about what these shapes think, right? And what they are. And they're exploiting your cultural contextual awareness. So they wrote this entire book on interpersonal communication that I think is still very insightful today. I have a copy of it in my office. But with this, well, Heidel did, with Simmel did this experiment, like, okay, now the big triangle's clearly very angry, and those two are frightened. Oh, and he's furious because they've escaped, and so he ends up breaking everything, right? So, you know, so this understanding of this is actually quite old, but it's funny how rarely it comes into computer science. Anyone know what this is? It's another apocryphal quote, actually. Supposedly Ernest Hemingway, yeah. It's Ernest Hemingway, I think, but it could be Kafka. Yeah, who knows? A 6-word novel. The start, beginning, and an end. And the idea is that in that there's an entire story behind those words, only 6 words, right? So the only reason there's a story is because you understand human context, you understand human life, you understand death, you understand what it means to have the expectation of life. Otherwise, there's only 72 bits of information, yeah? So this, you're thinking, what the hell has this got to do with data science? Well, because we've got to have conversations with computers now. Because we don't have a great model of the way the computer operates. Even you as computer scientists, I suspect some of you were like, oh my God, that is different, the transfer rate. This is a different architecture. So when we sort of try and communicate with the computer and it doesn't respond, and then it does that, and then eventually it says no, and then we swear at it. And that is basically the interface we're facing at the moment that data scientists are dealing with, and the problems that if you go this direction in your career that you'll have to address, that people don't know how to do well. Some people know how to do it better than others, but people don't know how to do it well. And it all comes from this evolved relationship with information. So lies, damn lies, and statistics is this narrow bandwidth channel between us and data. Yeah, so I present you data, I misrepresent, you see patterns. One of the things we do is we anthropomorphize things. I can't really say that. So I invented a new word, I call it anthrox, because pomorphize is replaced with X. So we anthrox things. So we're going around anthroxing things the whole time, assuming they're human. Our car won't start, it must be upset. You know, treating them as they're human, because that's how we communicate with objects. So we do that to varying degrees, just as humans, but we also do it, we tend to overinterpret even data. We don't look at the data and go, oh, that chart is feeling upset today, but we see patterns where there aren't patterns. So that's the lies, damn lies, and statistics. But the whole field is now being mediated by mathematical statistics. So when it comes to drugs companies wanting to deploy solutions, we say, well, let's see the results of your randomized controlled trial, you know, or when we see papers in journals, of course, there's things like p-value hacking and problems there. So we still have problems. We say, well, come on, give us the statistics. What's the p-value of this? What's the null hypothesis? You know, make sure that you're trying to draw conclusions in a valid way. That's the field of mathematical statistics. The new phenomena is this, that massive Jeff Bezos once every 2 months salary there, and that low bandwidth here. Now, of course, you might say, but we've got vision. Yeah, there's a few things more we can do. I think each optic nerve is 1 megabit per second. So even if you take your most high bandwidth input, and you can't output through your optic nerves, right? So you can't project back. You're only at 1 megabit or maybe megabyte. And there was a paper on that was really cool. It's a very cool thought, isn't it? That that's all you've got. I mean, and so how are you doing this whole image? Well, actually, your eyes dance around the image and then your brain fills it in, is what's going on. So very, very low bandwidth, even when you look at vision, which is unidirectional. Here, I'm thinking sort of bidirectional when I say 2000 bits per minute. So this is the way I see the world. That's classical statistics, or it was the motivator for original classical statistics, mathematical statistics. And this is the challenge of data science. Now, of course, all the lessons we learned in classical statistics are still good for bringing into these challenges of data science. But you now need to go from the data through the computer all the way to the human to represent what's going on. And as computer scientists, you're obviously well positioned to do that. But as computer scientists, you also need to show an immense amount of respect for people who've thought about this for over 100 years. And even more importantly, I think the most important thing you'll see in any of these things, the domain experts, the people who understand the context, people who've spent their lives thinking about chemistry or physics or economics or policy or public health or epidemiology, and what knowledge that contextual information brings to the equation so that you understand how to communicate those things well. Does that make sense? So big data is this pervasive phenomenon that's affecting all aspects of our lives. And I mean, what we're seeing, even if we think of things like what's going on with Facebook, at the moment, and social media, these effects are not even, it's not like, I always sort of like to say to people, it would be great if like Mark Zuckerberg was evil and had planned this. I mean, I just think I think he's quite naive, but he's not evil. It's a phenomenon. And if you take Mark Zuckerberg and Facebook out of the equation, the phenomenon will reappear, because what you're doing is you're closing the loop between the human, the computer, and the data, and iterating that loop with A/B tests, which are, from classical statistics, randomized controlled trials, to try and work out ways where you can increase the interactivity of the human and the machine, right? So it's not surprising that through doing that, the machine discovers things with these very high bandwidth connections about the human that we don't even know about ourselves, like what we're attracted to. And then we end up having to study the phenomenon, but the computer has understood this ages ago. Of course, what does understood mean? It doesn't understand it in a conscious way that it can explain it to us, but the ecosystem we've developed understands how to do that. It understands how to increase interaction, and it knows that the way you do that is you tell people things they like to hear. Yeah, I mean, work that out. It's not that surprising in retrospect. So I sometimes it's quite funny, because when you look at nutrition, this sort of happened over like about 100 years. Once people could start manufacturing artificial foods, quite quickly people realized, hey, if you put high fructose corn syrup in things, people consume it. Yeah. And, so let's put that all in the soft drinks. It's cheap and addictive in some way. And now all our foods contain high fructose corn syrup. Well, it took how long? I don't know, 80 years for them all to discover that. And now we have a problem with, the sort of processed foods. You can think of social media as the cognitive equivalent of high fructose corn syrup. The machines, because of that high bandwidth connection, were able to discover what we responded to, which is validation. People liked your post, and things that sit with the way you like. And that's created quite a fractured society very, very quickly. And it's because that this cycle can run much, much quicker now. I mean, we've studied, advertisers have studied this stuff for ages, but they didn't have it quite as refined in that way. But, it would be nice, as I say, if we could say, well, so therefore the people in charge of these companies are evil. Maybe they are, maybe they aren't, but getting rid of them doesn't actually fix this, because it's a phenomenological problem associated with this fast iterating cycle. And if you're going to fix it there, it will just reappear anywhere. And if you're going to be data scientists, are going to be part of the problem. So understanding that is also important. So we can sort of see how this is sort of emerges. I like to talk about this. Has anyone here seen the Gartner hype cycle before? People love to put it up in business meetings and things like that. I want to see, they put technologies on it, like Gartner does this report every year. And I really want to see, where is the Gartner hype cycle on the Gartner hype cycle? The notion is is it's an idea that all technologies come in and then expectations go high, and then it disappoints, and then they go low, and everyone says that's rubbish, it never worked, you know. So like 2016, everyone's saying AI is amazing, and then like, I don't know, now people are saying it's terrible, I don't know, but the idea is they work, and then actually you work out how it works. And my knowledge, my feeling is like, you understand you're on the plateau of productivity when people shut up about the technology. No one actually goes on saying, we're going to use cars, or we've got an innovative approach using cars and computers and watches to get together and play a football match. No, they don't say that, because obviously you're going to do that because all those technologies work. When they say we're going to use AI to solve something, they say that because that technology doesn't work. So that's why you talk about it, because you have to think about it. Here we go. So here we go. So I think you're doing the same thing as me. So was that Google Trends? The Gartner hype cycle. Oh, brilliant. Oh, yeah, I've done that one as well. Yeah, you can do, yeah. So this is how you do it as computer scientists, just as you've done. Brilliant. You can search for Google Trends for these different terms and see what people are saying, and you can do that for the Gartner hype cycle, which was just dipping, as we saw in that plot, because it's not as good as we thought it was. So here, what I'm showing you, in fact, let's just cycle through them individually, is artificial intelligence and the Google Trends. And what you sort of see is that I don't know what AI does. I was in the meeting where Mark Zuckerberg was there and Jan LeCun was there, and they launched the Facebook AI Labs. And when they said, oh, we're calling it Facebook AI Research, I was like, oh God, because that's the technology trigger for when we started calling machine learning AI, which utterly depressed me, because AI means so many different things to different people. And it's not a well-defined term. It's an interesting term, but it's not a useful term for describing technically what you're doing. But of course, historically, the other reason I didn't like it is historically AI was nothing to do with machine learning. It was all about these sort of expert systems and, you know, programming languages for expert systems, and actually utterly rejected machine learning. But we can look at big data as well. And that was a term that entered a government report in about, I don't know, 2012. And you can see what happened to it. It sort of went flying up, but it's already sort of tailing off and going down. People don't tend to say big data anymore. I do like to. I was saying to someone the other day, we should not create an AI institute at Cambridge, because if you look at Oxford, they've got an institute in every term that was a hip and happening term for a few years. The Oxford Internet Institute, the Oxford Big Data Institute, and donors love that. They want to donate that. But I'm thinking, like, wouldn't it be cool to not have an AI institute in Cambridge, even though all the donors want to give money for that? But maybe we will. But we don't want a big data institute anymore, because we're not saying big data anymore. That term's becoming passé. You might think it's becoming passé, only when you look at some of these other terms. Well, so what was going on here? What was the data stuff? Well, it's interesting if you look at data mining, but no one says that anymore. Data mining sort of collapsed as a term, which I find odd, because it's sort of still as important as it was. It's cultural and it's community driven. People who used to talk about data mining tended to be people who were looking at databases directly, working very closely with databases. And somehow, as you're going to find out when you do the practical, if you're constrained to SQL queries to do your analysis, it's a very small window on the world and very hard to do interesting analysis. So a lot of the data mining things were things that were fast to do sort of on databases and quick to do. And they're still being done, I'm sure, but people just don't go on about it anymore, because either there's a part of it that's working and a part of it that was useless. The part of it's working, we don't talk about. Part of it that is useless, we don't talk about either. So that term's sort of gone away. But then here's the sort of deep learning, which interestingly, the sort of big new results were about 2012. The field was around all across this time. Certainly, that's the period when I really enjoyed deep learning meetings, because they were the sort of interesting sounding crackpots that no one was listening to. And then ImageNet's here, and now of course everyone's doing deep learning, and their dog and their cat as well. So it's sort of, but it's interesting that it is seeming to drop. When I first showed these plots, neither deep learning was not dropping, and machine learning which is just like a sort of larger scale version of deep learning. Weird that it's crossed AI. So that sometimes like, when I see things like that, I'd stop trusting Google Trends. That seems odd to me. These are supposed to be, because you put the terms in together, they're all supposed to be normalized to 100. But I can't believe more people are searching for machine learning than artificial intelligence. That doesn't sound right, you know, because kids will search for artificial. I mean, they may search for machine learning, but not as much as AI. So that's the sort of what we see here is a bunch of data-driven technologies sort of coming in and out of fashion. But we're in a world where we haven't quite stabilized in what we're going to call those set of techniques. My hope, and my hope ever since we killed big data as a term, has been that data science will be that term. The thing that is actually the serious study of these things rather than it's the hype flavor of the month, and that will actually end up making some progress in. But I might be wrong. You can't control this stuff, you know. Okay, so what is machine learning? Because that's a sort of key component of this whole revolution. Well, anyone who's seen any lecture course I give, I always end up putting this, not really an equation, but this little formula. To me, machine learning is the combination of some data with a model and some computation to make a prediction. And the reason why we're seeing new phenomena around it is not because we got super clever with the model. I would like to say it's because me and my community were really clever.
So I think the reason why you got machine learning is for the search term, not the field of study. So if people were searching AI, that wouldn't show up. So yeah.
So if you do AI as well.
So the green is artificial intelligence search term, yellow is machine learning search term, red is machine learning search.
That's good. So if you manage to get the field, then it comes up better. Yeah, because you mean most people search for AI when that makes a lot of sense. Yeah, but then my plot wouldn't be very clear anymore. Because AI, just to sort of be clear, AI was so much ahead. Yeah, I was totally right. So by the way, skepticism about data, I've been showing that plot for ages, and I'm not even doing the thing that I should do, which is to do exactly what was done here. And I set this up. This is an example of data science in action. If there's something in your head that says that's a funny result, it seems a little bit odd that AI is less searched for than machine learning, which I actually said. And it's on my damn plot, it's a funny result. And yet I've been presenting that plot for 4 years. And exactly what was done here was the right thing. I wonder if there's something else in the data that is causing that problem. Never doubt your understanding of context or the domain experts' understanding of context. Always follow it up. So, because that's a bug. That's a bug in my analysis. And that's the sort of thing that you need to start trusting, how to see those bugs in your analysis and how to overcome them and get the analysis right. Brilliant. I like that. Well done. Thank you. So data plus model to compute leads to prediction. Now, I use this formula and I think that it's totally justified to say, well, this formula's, everyone's kind of doing this. A statistician is doing this, but they tend to focus much more on the interpretability of the model than a machine learner. So I tend to focus on the quality of the prediction, but then I can't explain why I'm making that prediction to a policymaker. And then that's not very useful, but it's quite useful if I'm trying to recognize, I don't know, faces or whatever I'm trying to do. I'm doing ImageNet, right? Physics is trying to do this, but they tend to put much more mechanism in their models, right? It's still a model, differential equation stuff. They put a lot of physical understanding in the model. And we've got another course that you can do next year if you stay for part 3, ML and the physical world, which is all about that interface. So this is a very common thing, but it's also very general, right? So data can be anything. It can be observations. They can be actively or passively acquired. There's different types of data. There's surveillance data. There's observational data. There's what I call happenstance data, the data that's just out there and about. And that's the kind of challenge that you're facing today. It can be data about data, metadata, right? Everything is data in some sense. By the way, anyone French here? No? Speak French? What's French for data? No? Oh, good, I can make it up now. I can tell you anything. So in French, it's, I think, les données, as in the givens. And of course, data is coming from Latin dare. So for some reason, we've got the Latin. So another way of thinking about data is it's like the givens. This is what you're given. Yeah. The model is where you bring in a lot of your assumptions in. So it could be based on previous experience, your models. I mean, we're often using smoothness assumptions. I like to think about the model as it's your beliefs about the regularities of the universe. And very often they're reflecting inductive biases. Humans have a lot of inductive biases, some of which we've been talking about around anthroxing. I'm not going to say anthroxing things. Yeah. So inductive biases, but that's quite hard to model human inductive biases. That's, whole fields of study look at that. And then the prediction could be an action to be taken, categorization or quality score. It could be anything, right? Now, one can argue that you can take decision-making outside of this, right? So you make your prediction. I mean, this certainly comes up with doing quite a lot of policy advice recently, where you're trying to make predictions. We see that with all the epidemiological models. This is what we predict is going to happen to COVID. The decision about what to do about that is kept separate. Now, if you conflate that, the decision-making, you get sort of reinforcement learning or control algorithms and these sort of things where you take action on the basis of the prediction. So one can view that as part of machine learning or not as well. Operations research does a lot of decision-making based on modeling as well. Economics, these different fields, all will interface with data science. So there's still this report which was convened a while ago, Machine Learning, the Power and Promise of Learning from Data, which is off the bottom of the screen, which I still think is a great report summarizing that. But you're probably all more familiar with machine learning than the average person in the street. But to combine that, we need a couple of things. We need a prediction function. That's what this isn't universal. We don't always use a prediction function, but if you look at most machine learning algorithms, they're built on two things. One is a prediction function that embodies our beliefs about the regularities of the universe. And the other is our objective function. And the objective function, that measures the cost of misprediction. So the cost of misprediction is something so ironically, it's an objective function, but it's highly subjective. Because it's what the machine learner makes up in their dark bedroom in the middle of COVID, without any of their understanding of society and the downstream effects of that. And one of the things that you see happening an enormous amount is we're trying to normally minimize the average expected cost of this objective function. But that means we're ignoring worst case costs. So, for example, in control engineering, where a lot of this stuff is effectively being done, you'll see a lot of work on what's the worst case. What can you prove about your controller? That's because the worst case is that the plane falls out of the sky, right? Now, when you're looking at the Amazon supply chain and you're looking at average case cost, the worst case thing that happens is you get 25 million fidget spinners turning up at the Newark fulfillment center. No one dies, but it's still not good. And unfortunately, almost all of machine learning is based on average case. And so this can have quite extreme effects. When we look at societal effects from machine learning, we look at bias. Bias can come in two places. It can come from the model, it can come from the data. There's the only two ingredients, so it can come in both places. And then some average fit to what the average population is. Oh, and surprise, surprise, minorities are disadvantaged by doing that because we aren't looking at the worst case, what it was going to do to some parts of the population. We were looking at the average case, which is dominated by the majority. So it's no surprise that comes up again and again and again. So I tend to see the model as composing of those two things. So you could have bias in these things coming from the data, the prediction function, or the objective function. It's everywhere, right? By the end of this, you'll never want to do any machine learning or data analysis once you discover how hard it is. But what is fundamentally going on? So we're just automating things. We're automating cognitive process, right? So automation scales by taking processes, codifying them and automating them. And the new phenomenon with machine learning is, it turns out that we just have to acquire a lot of data from the process and then fit it to a neural network. And now we can automate that. Before we had to sit down and program it. What a pain. Now we just have to get a lot of data and run TensorFlow and tell everyone it's the brain. That's why you're seeing it so pervasive, and you're seeing it deployed extremely quickly, more quickly than, I think software, also the world, everything's connected. So these are sort of causing problems. In order to do that, you basically need a bunch of interconnected components and compatible components. And you're seeing this particularly with neural networks. There's a load of software that allows you to interconnect layers and express what you think about the world in one piece of software and build a very capable functioning model very, very quickly. I mean, that's a major change in the way we do machine learning versus, say, 10 years ago. And you can sort of compare it to what happened in manufacturing when Colt, I think, did the first ever production line. There's a Colt 45 becomes very popular because of that, or the Ford Model T. These were interconnected components, screws that were manufactured to a standard and then pieced together. So whenever you are part of an automating pipeline, then you'll find that that's the thing that you start to try and do. I'm gonna just see what I've got next. I won't go through that slide because what I'll do is we've only got just a minute. So make sure we give time for the next people to come in, to sort of pause there and just see if there are any questions about what I'm saying so far. So I'm trying to sort of set this landscape and give you an idea of the components, which is data, compute, and machine learning technologies. And these things are now coming together to do data-driven decision-making in society. And this course is to teach you about how that is being done and how we would like to do it better. But let me just, I'll stop the recording and then see if there's any questions on anything I've said so far about that, or practical, or the